In this segment, we'll start our detailed look at SQL column types, covering numerical types first. Numerical column types fall into roughly three categories: integer types, floating point types, and decimal or numeric types, which are sort of in between the other two categories. So let's start with integer types. You can declare a column to be an integer with the SQL standard integer, or synonymously and more commonly int. In SQL, as in other programming contexts, there's a trade-off between the number of storage bytes an integer uses and the minimum and maximum values that you can store in the integer. SQL int fields are 4-byte signed integers, and that means they have a value range from a minimum of -2 billion to a maximum of a little over 2 billion. Question 1 then. The standard int suffices for most purposes, but if you're storing huge numbers, you might want a bigger range. Or if you're scrimping for space, you may want a column that takes fewer bytes at the cost of a smaller numerical range. There are other choices for size in bytes and range of an integer. What are the MySQL int types that use 1, 2, 3, and 8 bytes? And all of those choices are possible. And how many of these are in the SQL standard? The MySQL manual, chapter on data types, will be of use, and Wikipedia's SQL article does a pretty good job of describing the SQL standard itself. And after a bit of research there, you should come up with tiny int, small int, medium int, and big int, respectively. Of these, only small int, which is 2 bytes, and big int, which is 8 bytes, are SQL standard. And if that's not enough of a selection, you can also declare any integer type as unsigned. I'll add that briefly here just to show you what I mean. Thus, for the hardware-oriented, this has the same effect as it does in C or C++. What would have been a 2's complement negative value instead becomes a large positive value. And for everyone else, it's enough just to know that unsigned doubles the positive range of the integer without increasing the space used, but at the expense or benefit, as we discussed in an earlier lecture on preventing human errors, of not being able to store negative values at all. Now, if you're not into binary math, 2's complement, and the like, the following small table, which I'll actually put up on the slide here, will pretty much cover you. It's really all you need to choose between the integer types. So from the notes directly here. And by the way, well, first, tiny int, 1 byte, min and max value as stated, -128 to 127. Small int, now you're using 2 bytes, get a bit better value range. For modest counts, like, I don't know, number of items in a receipt, for instance, would be a reasonable thing there. For medium int, you get to minus and plus 16 million or so. They cover a lot of possible values, but int is the more standard one, and that is a very large range. And if you really need large numbers and you're representing the national debt or what have you, a big int is your choice there. And then if you add unsigned, just double the maximum value and change the min value to 0. If you really don't care, then just use int or possibly big int for really large values. A big int can literally count every grain of sand on the planet. And if that isn't sufficient, well, you just need to use smaller numbers. Now, sometimes you also see parenthesized numbers after the integer type, like the 11 here. These are formatting cues for displaying the column in text form. The parenthesized number gives a minimum number of columns for textual display. This doesn't affect the byte size or numerical range of the integer. And printed values that are too big for the field size will still get displayed accurately. SQL just expands the number of text columns as needed. It's rather like the field size in a C or Java printf format specifier, if you're familiar with those languages. So let's move on now to decimal types, like product price in Bakery 2. Now, these permit a fixed number of digits after the decimal point. If you declare a column as decimal 62, like this, or synonymously numeric 62, either one works, that means it holds decimal integer values of up to 6 digits, with 2 of the digits after the decimal point. Prices could be as high then as $9,999.99 given this declaration. And they would always have 2 digits, even if they're 00, after the decimal point. A minus sign is also allowed, by the way. And by the way, we do mean decimal. A decimal number is not stored in base 2. Instead, the database stores it in decimal form, typically cramming 2 digits into each byte. So a decimal 62 uses about 3 bytes. And the computations on such values are also done in decimal. To do math on decimal values, the DBMS runs code that performs in effect the same process that humans use in adding, subtracting, multiplying, or dividing decimal values by hand, complete with multiplication tables, decimal carrying and borrowing, and so forth. And all this leaves the question of why we'd represent integers this way. To see why, let's imagine, as a brief aside here, a following conversation between a computer and a human. So the machine starts. Let me get this straight. I can do 10 teraflops in binary, and you want me to store numbers and do computations in this monkey notation. Computing in decimal is tedious. And the human responds, well, tedious is your job. And given the millisecond disk access times, who cares about a few extra nanoseconds doing a computation in decimal? Binary is more compact. I can save you space if you let me use it. We're talking about disk here. I can buy several terabytes for the cost of a nice evening on the town. I'm really not worried about squeezing the most out of every bit. And the machine says, yeah, okay, but what's the advantage? Why not go for base 20? You can use your toes that way. Any decimal computation can be done just as well in binary, better in fact. And the human's question, and this is the important point, is, okay, genius, so what's 0.1 in binary? Machine says, well, I don't count on my fingers, so I use binary fractional place values. Your 1/10 is, let's see here, 1/16 plus 1/32 plus 1/256. That comes to 0.000110011. Yeah, okay. So it's a repeating binary fraction. No big deal. We'll round it off. Not if it represents a dollar amount, you won't. We monkeys have a thing about accuracy when it comes to money. Financial transactions have to be right on the dime, so to speak. The machine says, you throw pennies in the trash, for God's sake. You're telling me we can't have a little drift in a financial computation? Take it up with the SEC or the IRS if you doubt me. If it comes out evenly in decimal, you can't round it off. And then, ultimately, that is what it comes down to. Decimal types would probably not exist were it not for the fact that a fraction that comes out evenly in decimal often does not in binary, and financial and accounting usage and law do not tolerate rounding of calculations that come out exactly in decimal form. If you're storing monetary values, use decimal types. After the complexity of integer types, floating point types will seem mercifully simple. There are 2 standard SQL choices, float and double. Either one allows numerical value with decimal fraction parts. And unlike decimal, they offer fast computation and no restriction on digits to the right of the decimal point. Bakery 2 has no examples, but if we wanted to, for instance, add a weight to product, that would be a sensible use of float. Float and double offer a choice between accuracy and space used. Float uses 4 bytes, but has precision worse than a cheap calculator, about 7 decimal digits, while double uses 8 bytes and has good precision of around 16 decimal digits. Use float when you don't need much accuracy, for instance for a person's height in inches or for a weight of a product. Use double when you need more accuracy. MySQL also allows a parenthesized integer parameter after float or double. For instance, we could have written float 10 here. But this just adjusts the type to whichever choice, float or double, is needed for 10 digits of accuracy. So it really doesn't do anything you couldn't get by just choosing between the two. In the next segment, we'll look at column string types.